Okay, so what we're looking at right now is the application of Newton's second law and understanding that it's really the net forces that act on an object which are causing that object to accelerate. So the key part here is this word net force. Now, the word net force is simply the sum of all forces, but what's left over, right? Sum of all forces, or what we call the unbalanced forces. Because, as we mentioned before, unbalanced forces. So, before we talk about, it's the force that's acting on an object that causes it to accelerate. But it's not really. There could be thousands of forces pushing on an object, but if they all balance out, the object will maintain its state of rest or continue in a straight line at a constant speed. What we call, when we were talking about inertia. So it has to be an external unbalanced or external net force acting on an object that will cause it to accelerate. That point is so important. So when considering Newton's second law, it is the net or unbalanced force that causes that acceleration, that cause the acceleration of an object. If the forces acting on it are balanced, which means the net force is zero, the object will not accelerate. Okay, so that word not accelerate means it won't speed up, it won't slow down, nor will it change direction. So a couple things happen. Either it will, one, remain stationary. If it was already at rest, it'll stay at rest. Or two, it will continue, and people often forget this, it will continue at a constant speed, which by definition, think about it, is clearly Newton's first law. Object at rest will tend to stay at rest unless acted upon by an external force, or continue to constant speed, not change direction, or slow down or speed up, unless acted upon by an external force. So there's always two choices. Whenever you're doing your problems, don't assume it's always that it will stop moving. When the net forces on it are zero, or their forces are balanced, it just means that either it will remain stationary or will remain at a constant speed. It's very important. Mathematically, what this looks like is this for the situation. The F net, so this is one way of writing it. It is a vector, so we should include vector signs because it has direction associated with it, is equal to the sigma F. Now, sigma F is really important. This symbol sigma is the summation sign. And what it means is add up all the forces. If they're balanced, the acceleration is zero. If they are unbalanced, it's not zero. So these two things mean the same thing. F net is the same thing as sigma F, as in the case that there's a net force. So if they're equal to zero, meaning that the forces are balanced, or there's no net force, then this implies that the acceleration will be 0 meters per second. And as we wrote above, object will stay at rest. Or two, the object will keep moving at a constant speed. The easiest one to think about that is a car. If you're driving in a car and you take your foot off the gas, you slow down. The net force is not zero, which means you're slowing down or you're accelerating. But if you're moving at 100 kilometers an hour, right, you know that you have to press the gas, even though there's wind resistance and friction from the ground. You must apply a forward force that matches the backwards force, so the two forces are balanced in both directions, and you don't stop moving. You just move at a constant speed because you're no longer accelerating at that point. Okay. Newton's second law is a vector equation, extremely important. The acceleration is in the direction of the net force. That means that the net force, the unbalanced force, is north, the object will accelerate northward. If the unbalanced force is right 60 degrees forward, it will accelerate at right 60 degrees forward. If the net force is south, it will go south. If the net force is left, it will go left. It will accelerate left. It's very important. I mean, it's a vector equation, and since we know that, you know, Newton's second law says that the net force is equal to mass times acceleration. Whichever direction this force is in, this here must be in the same direction, right? I mean, they're on opposite sides of the equation sign. So if this one has a net directional force of right, then this acceleration must be right. And we can intuitively understand that as well. To determine the net unbalanced force, you simply add up the force vectors acting on the object. Be sure to choose the direction to be positive when we're looking in one-dimensional equations before adding up the forces. The sum of the forces always equals the mass times acceleration. That is Newton's second law. Newton discovered that, and it works out very well. So Newton's second law then looks like this. F net equals, now there's two options. You can write it as F net or you can write it as sigma F. They mean the same thing. Mass times acceleration. That's Newton's second law. So I wrote down below here, sum of the forces equals mass times acceleration. So that means sigma F is sum of, that's what this sigma is, and then obviously the forces is the F, equals mass times acceleration. Now I've left vector signs there, good. So that means if we have, you know, an n number of forces acting on an object, F1 plus F2 plus F3 plus dot 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 Fn. So that's just, maybe there's 10. We'd stop at 10. If there's 1,000, you stop at 1,000. Equals mass times acceleration. It's this simple. So what we're going to do now is actually look at a couple of examples where we're going to use this formula. I mean, it's just Newton's second law. It's not anything fancy here in this case. But we're going to add up the force vectors acting on an object and see how it causes the object to accelerate. And really, we're just looking for different solutions to different problems. Okay, so doing this, here's the situation here, and you've got it on your sheet as well. You know, what we're going to draw, and when we're solving these types of problems, we're going to create something that's really important to understand, and that is the concept of a free body diagram. So we often call this, and write this nice and big on the top of your sheet, FBD equals free body diagram. Okay, that is really, really important. FBD stands for free body diagram. It means draw an object, whether it's, you know, we're just going to draw it as a circle or a box. Some places do boxes, some do circles, doesn't matter. Some places just do a dot, so there's all different ways of doing this. It's just, if you draw just a single dot, it's hard to draw the force vectors acting on it. You don't have to draw the object in there. I just like to do that for fun. So a free body diagram is a way of representing an object, and then you can draw the forces acting on that object external from any other objects. So it's, you're focusing on one particular object, and you think about and draw on the forces acting on only that object. Now, before we get into friction and things like that, all we're going to focus on now is we're going to ignore gravity, and we're going to ignore the force of the road acting, or the force of the ground acting on this object. So we're going to have no up or down forces for these types of problems to start. We will get into that later. All we're going to look at is a one-dimensional problem, so 1D problems. Okay, and I gave a hint here. Make sure you always pick a direction to be positive, and to make your life easy, make the direction usually in the direction of the acceleration. So it says, analyze the following situation. Note, all solutions must follow the format given below. Show all work. Okay, here we have a skateboard. The free body diagram I've drawn is just the circle with this in it. Now, what we typically do is, you know, we've got the mass equals 3 kilograms. So we write out what the mass is, typically with a lowercase m, but it doesn't matter in this case. We've got an F1. Now notice, the subscripts are really important. Don't start just throwing F, 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 F everywhere. You want subscripts on them so you can differentiate between which forces are which. Here we've got the arrow. I'm going to pick the positive direction to be to the right, in the direction of the acceleration. I'll show why that's important afterwards. Now, since this is a vector question, we know that anything in this direction will be represented as a positive value. Anything in this direction will be represented with a negative value. So the way I'm going to do this, and there's multiple different ways of doing this, we're going to write this as Newton's second law. So we're trying to discover what the acceleration is. So it's sigma F equals ma. Okay. Now we could write out the force vectors. We could say F1 vector plus F2 vector plus F3 vector equals ma vector. And then we can work out the signs afterwards, thinking about the positives and negatives. But what I'm going to do in the next step is I'm going to drop the vector sign, and I'm going to pick the directions based on the diagram already here. So F1 is in the positive direction because it's pointing to the right. So I'm going to write F1 plus F2. This one's pointing left, which is in the negative direction, minus F3 equals ma. Now I've dropped the vector signs because I've put in the positive and negatives already. If I left the vector signs, this would actually be F1 vector plus F2 vector plus F3 vector. And then when I substitute the values in, I would replace it with plus 15, plus 7, minus 3. And it would work out the same way. By reducing it and dropping the vector sign, I'm just saying I know this is in the positive, and I know that's in the negative, so all the signs will work out. Regardless of which convention you choose, the signs will always work. Now to solve for this, I want the acceleration by itself. So simply, if I divide both sides by mass, I will achieve that. There we go. So the top part, F1, when we're looking at this, is 15 newtons plus F2, which is 7 newtons, minus 3 newtons divided by the mass, which is 3, is the acceleration. Now the top, I'm just going to add the top up. I'm going to go through this slowly. 15 plus 7, or 15 plus 4 is 19 newtons. And the bottom is 3 kilograms. That's what the acceleration reduces down to. Now the reason I did this is because I wanted to point out that this top part here, this 19 newtons, this is our net unbalanced force. And this clearly is the mass. So 19 is what the net unbalanced force is acting on this. So we know that it's going to accelerate. It is not going to stay at rest or move at a constant speed. It is going to be accelerating, and since we ended up with a positive number, we know that it's accelerating to the right. And you can see that 15 and 7, these are bigger than this one. So 15 plus 7 is 22, subtract 3 is 19. So we know that the net force is to 19 newtons to the right. And the mass is 3 kilograms. Now remember, a newton is a kilogram meter per second, or a newton times meter per second, kilogram meter per second squared. So the kilograms are going to divide out. We're going to be left with the acceleration. So the acceleration we end up with is approximately 6.3 meters per second right. Now I could have left out the right simply because we have a positive sign here, and we already chose the direction to be positive. So by definition, getting a positive answer would have told us that was right. Now some of you may forget, and you may not choose this direction to be positive, the acceleration. You may choose the opposite direction. Well, what would that have done? Well, not much. It would have made this negative, positive. And what you would have ended up with here is you would have got a negative acceleration, which means that it was a negative acceleration to the left, which is a positive acceleration to the right. So you would have got the same result, except for with the minus sign. But it means the same thing, and that's so important to understand. In the second one, we're trying to discover the value of F3 acting on an object, knowing that the force combination that we have here is causing an acceleration to the left of 2 meters per second on a mass that is 2 kilograms in value. So we start sigma F equals ma. Positive is that way, so we have F1 minus F2 minus F3 equals ma. Since we're solving for F3, I'm going to leave it here and bring the other stuff to the other side. Now because it's added, this one's added, so I subtract it. This one's subtracted, so I add it. Now this minus sign, we can leave it there, or we can just switch by multiplying by -1 across the whole thing. We call it switching the signs, but it's not really, that's not a great terminology to use. We're multiplying by -1 or dividing by -1 across all terms. So we get this situation. Okay. Now, what we get from this is we see that F3 is equal to negative, so M1 is, the mass is 2, acceleration is 2, plus F1, which was 25 newtons, minus F2, which is 10 newtons. Now what you'll notice is this value of mass times acceleration is by definition a newton. So this is minus 4 newtons is the net force, plus 25 minus 10. So this little piece here, this is our net force. We knew that the net force in this case was 4 newtons. Okay, not -4, but it was 4 newtons. So if we add this up, that 15 minus 4 is 11 newtons. So F3 is 11 newtons. Okay. Another way of looking at this. Okay, this is called a general solution, and you should be solving for these general solutions. It's the better way to do things. The general solution shows that you know what you're doing, you know all the math, and the rest of it's plugging in numbers. So that's it's very good to be able to recognize and to be able to derive this net or general solution. Just like we did up above, the general solution for the question above, and you can write this down right here, this was the general solution for this problem. Okay, and you need to work on doing this. Plugging in the numbers is whatever, who cares? You get your number, that's fine, but getting to this point shows you understand the physics of it. So another way of looking at this is going back to this beginning line, just for a little help understanding everything here. So it's F1 minus F2 minus F3 equals MA. Well, if I plug in my numbers now, 25 minus 10 minus F3 equals 2 times 2. 25 minus 10 is 15 newtons, minus F3 has to equal 4 newtons. This number, 4 newtons, that is our net force. So it wasn't the minus 4. Remember I said that before. The net force is really just the number. So this net force of 4 newtons says whatever these two, the 15 newtons, because those are easy to get from the 15 and the 25, that 15 newtons, whatever number you subtract, meaning whatever force this value is, must result in a 4 newton difference. Well, clearly that means that F3 is 11 newtons. The same answer, right? So you look over here and you say 11 plus 10, 21. 25 minus 21 is 4, which is the net force, which means that it's correct. So it's super important to understand that. Again, if you had picked positive to be the other direction, you get a tough situation. If you had picked the opposite direction to be positive, when you came to substituting in your numbers here, this should be in brackets, this should be in brackets, when you came to substituting this in, you would have found that this would have been negative, positive, positive. But what most people forget is that you wouldn't write MA. Because if you chose the direction in the opposite direction, this would be negative, positive, positive, negative. And you would have to include that. And then it would all work out. That is a very, very common mistake. So that's why we always tend to pick the positive direction in the direction of the acceleration. So if you don't know the direction of the acceleration, pick a direction, make it positive. If it comes out negative, it just means it was going or accelerating the opposite direction. That's a very important nuance of this situation, something we're going to really touch on a lot in some of the other problems when you start to get used to doing these types of problems. So that's it. That is Newton's second law in terms of what are net forces and how do we use them. And using this tutorial, you're going to finish off all the problems from the problem booklet and prepare for a quiz in this part of the unit.